So, have you ever wondered what's actually going on inside a machine learning system? Well, in this explainer, we're going to strip it all back to the absolute fundamentals. We'll get into the core components that make everything, from your spam filter to those recommendation engines, really tick. So, what are the true building blocks of machine learning? I know it can seem really complex from the outside, but it actually boils down to just a few key ingredients working together. So, let's break them down one by one. Okay, let's dive right in. The first, and honestly, you could argue the most important building block is data. Just think of it like this. Data is the essential fuel that powers the entire machine learning engine. Without it, you're going nowhere. And surprisingly, the starting point for most machine learning is actually pretty simple. It's something called rectangular data. And don't worry, that's just a fancy term for what's basically a spreadsheet. You've got rows and you've got columns. Each row is a unique case, like a single customer or a house that's for sale. And each column, that's a feature, which is just a piece of info about that case, like their age or the home's square footage. And this brings us to what I'd call the first, absolutely non-negotiable principle of machine learning. Without data, there is simply nothing to learn from. The data is what gives the algorithm its raw examples, its experiences, if you will. It's from this data that the machine can even begin to see any kind of pattern. It is, without a doubt, the absolute starting point. So here's how it all fits together in the core process. First, you start with the data, right? You take that data and you feed it into an algorithm, which really is just a set of rules, kind of like a recipe for finding patterns. What comes out the other side is a trained model, and that model is now your custom-built tool ready to make a prediction the next time it sees some new, unfamiliar info. Okay, so we've got our fuel, the data, but what's the recipe? How does the machine actually learn from all that data? Well, it turns out there are two main ways this happens. So on one side, you've got what's called supervised learning. This is where your data is all nice and labeled. It basically comes with the correct answers already included. The whole point here is to predict a specific outcome. A classic example of this is linear regression. Then on the other side, you have unsupervised learning. This is where you're working with unlabeled data, no answer key. So the goal isn't to predict a known answer, but to just find hidden structures and figure out how the data is organized. Think k-means clustering. Let's dig a little deeper into supervised learning, okay? The best way to think about it is like studying for a test with an answer key in your hand. The algorithm gets shown thousands, maybe millions of examples where the correct answer is already known. So for example, if you wanted to build a spam filter, you feed it a ton of emails that are already marked spam or not spam. It learns the patterns from all those correct examples so that later it can make a really good educated guess on a brand new email it's never seen before. Okay, so the machine has its fuel, which is the data, and it's got a recipe, the learning type. But how does it know if it's doing a good job, right? How does it even measure its own success along the way? Well, the answer is something called an objective function. And the absolute easiest way to think about this is as a scorecard. Seriously, its only job is to measure how well the model is doing by calculating how big its prediction errors are. It basically gives the model a score for how wrong it is, and then the model's entire job is to try and make that score better. Now, don't let the math on this slide scare you, okay? This is just a classic objective function from a really common method called linear regression. All this formula, the residual sum of squares, is really doing is calculating the difference, the gap between the true real-world answers, which is that y you see, and the model's predictions. That's it. And the model's one and only goal is to make that final number as tiny as possible, as close to 0 as it can get. And that right there is the key. The entire learning process, when you boil it all down, is just one big optimization problem. The model is just relentlessly tweaking its internal settings, running thousands and thousands of tiny experiments, all with one single goal in mind: get that error score from the objective function as low as it can possibly go. But here's the thing, just getting a low error score on the data it already trained on, that's not enough, not even close. The true goal of learning is something much deeper. It's really the difference between being genuinely smart and just being really, really good at memorizing things. And that, right there, is the critical difference between generalization and memorization. Think of it this way. Generalization is like when you truly learn and understand a subject. The model gets the underlying patterns, the core principles. Memorization, on the other hand, well, that's like cramming for a test the night before. The model just recalls specific examples it was shown, but it has no real understanding. And a model that generalizes, it can solve new problems. A model that only memorizes, it's going to fall apart the second it sees something new. This leads us directly to one of the biggest pitfalls in all of machine learning. It's called overfitting. So when a model perfectly memorizes the training data, maybe even gets a 0 error score, that's actually a huge red flag. It means that it hasn't learned the real underlying pattern, what we call the signal. Instead, it's memorized all the random quirks and static and irrelevant details. That's the noise. So what happens? The moment that overfit model sees new data from the real world, it's totally lost. So why is generalization the absolute most critical goal? It's because a model is only valuable if it works in the real world, on data it has never, ever seen before. That is the only test that truly matters. A model that just memorized its training data is completely useless out in the wild. I mean, just imagine a medical diagnosis model that only memorized old patient files. With a new patient, it wouldn't just be wrong, it could be fatally wrong. Alright, that was a lot, so let's bring it all back together and do a quick recap of the fundamental building blocks we've just put in place. So, here's the whole process in a nutshell. It all starts with data, that's our fuel. Then we use a learning type, like supervised or unsupervised, that's our recipe. We need an objective function, that's our compass, telling the model how it's doing by measuring its error. The true north on that compass is always generalization, right? Real learning, not just memorizing. And why do we do all of this? For one reason, to make accurate predictions on new data that the model has never seen before. And there you have it. These components, data, learning type, objective function, generalization, and prediction, they're truly at the heart of nearly every single machine learning system you're ever going to encounter. So the question this leaves us with is a really exciting one. Now that you know the fundamental parts, what can you build?